Hello everyone, welcome to Chem 9. Today we will begin our journey to learn health science chemistry. We will begin chapter number 1 today, and in this chapter we will learn about matter, energy and measurements. This chapter is divided into 5 subcategories. In first section we will discuss what is matter and what is energy. In second section, we will discuss about various units and measurements. And in third section, we will discuss about what are significant figures and how we apply significant figures when we measure any quantity, and when we perform any calculations, how the answers are reported in correct sig figs. In fourth section, we will discuss about what is dimensional analysis. Just to give you some idea, in dimensional analysis, we convert any quantity from one unit to another unit, or in other words, we convert it from one dimension to another dimension. That's why it's called dimensional analysis. And finally, we'll discuss about what are various temperature scales and how we can convert from one unit of temperature to another. Broadly speaking, chemistry is a study of chemicals. However, we can define chemistry in other ways also. According to one definition, chemistry is the study of matter, changes in matter, and energy associated with those changes. In science, matter is defined as any thing that has mass and it takes a space. For example, any object around you, which may include table, chair, your book, or even air, or water, or food, they all are matter because they have mass and they take up space. So therefore, matter is all the stuff around you and in you. We often refer to a specific type of matter, such as aspirin, blood, or air, as a substance. Matter is found in 3 states. These states are solid, liquid, and gas. Examples of these 3 states can be found inside our body. The air we breathe is in gas state. Our blood and other bodily fluids are liquid, and bones and skins and flesh, they are solid state. In chemistry, we study matter and changes in matter at the atomic scale, that is, the scale which we cannot see. The better understanding of matter at atomic scale help us to understand all the changes happening at macroscopic scale. Now, macroscopic scale is the scale which we can see. For example, we can see 3 different bottles here, and all of these bottles contains a substance, or we can say orange looking substance inside here. And as we can see, the first bottle contains solid, and second one contains liquid, and third one contains gas. Now, experimental evidences have shown that matter is composed of small particles. And in next chapter, we will learn about those particles. Those particles can either be atoms or molecules, but let's forget about what those are. So at this point, we can say that all matter is composed of some small particles. Now, evidences have shown that at atomic scale, in solid state, all these tiny particles are closely packed together, and they are held together with strong interactions, hence they cannot move. Now, because they cannot move, that's why at macroscopic level we observe solid as a substance which has a definite shape and its volume does not change. Now, at atomic scale, if we look at the liquid state, we will see that in liquid state, the particles are not as rigidly connected to each other, hence they can move around. Therefore, liquid does not have any fixed shape. Similarly, experimental evidences have shown that in gas state, the interactions between particles is minimum. Uh, Therefore, these particles can move away from each other and they are quite fluid. Hence, gases do not have any fixed shape or they don't even have any fixed volume. As we know that matter is made up of particles, and in previous slide we saw that all solids, liquids and gases are made up of small spherical particles. Now those particles are not stationary, they are moving. Although in solid it looked like that the particles are fixed or stationary, but in reality they are not. They are vibrating, slightly they are vibrating. And in liquid, of course, particles move faster than solids, and in gases, these particles move quite a bit and they randomly collide with each other as well as with the walls of the container. Now, the speed by which any particle is moving depends on its energy. So as we can see that particles in solid are moving very little, so we can say that they possess very little energy. And in case of gases, because particles are moving a lot, therefore the energy which they possess is also greater than solids. In science, energy is defined as capacity to do work, and work is defined as an act of moving an object against an opposing force. So therefore we can see that in this picture, the nurse or the guy who's helping the patient is doing the work because it is moving the object, which is the chair, against an opposing force. So opposing force is gravity, or it may also be friction. There are many different types of energies. The most common ones are thermal energy, nuclear energy, chemical energy, gravitational. However, energy has two basic types, and these two basic types are kinetic energy and potential energy. Kinetic energy is energy due to motion. Kinetic energy applies to both moving objects in macroscopic scale and to moving particles, that is, the atomic scale. For a given substance, the particles are moving faster when that substance is in gas phase or gaseous state. So we can say that particles in gas state have more kinetic energy as compared to solid state. Potential energy, on the other hand, is the stored energy in any object. All matter possess potential energy as a result of its position or composition. So potential energy is stored within the matter. So previously we learned that kinetic energy is energy of motion. That is, it is due to the motion of any particle or any object. If the object is stationary, it possesses no kinetic energy. For example, bullet inside the gun does not have any kinetic energy. However, it does contain a lot of potential energy. But when we fire the bullet, now the bullet is moving, and because of this motion, bullet has a lot of kinetic energy, and when this bullet hits an object, that kinetic energy is transferred to that object, which does the damage. We also learned that particles in solids, liquids or gases are always moving, although They may appear stationary in case of solid state, but they are still vibrating, or they do possess some kind of a motion. Temperature is the measure of the average kinetic energy of particles of matter. So, if the particles are moving a lot, then they will possess higher average kinetic energy. Higher average kinetic energy means that temperature will be higher. Uh, so in other words, we can state that a substance that has particles with greater average kinetic energy will have a higher temperature. Now we know that particles move faster in gas state. Therefore, they will have higher average kinetic energy in gas state, and hence gas state will have higher temperature. Heat is defined as transfer of kinetic energy from one matter to another matter. Now, what does that mean? So let me explain. So for example, let's imagine we have a matter contained in this box, and as we know that matter is made up of particles, so imagine that these are the particles which make up this matter. Now all particles are always in motion, as we learned earlier. So as they are moving, so they possess some kinetic energy. So imagine that this matter is moving quite a bit. So these arrows represent that these particles are moving and their speeds are quite a quite a bit, and they are randomly moving in all directions. So so when they move, they collide with each other, they collide with the walls of container, all kind of collisions take place. Now if this matter comes in contact with another matter, as represented by this blue box, and this blue box matter is made up of, imagine, blue particles. Now blue particles are also moving, so maybe they are moving less, so very little. Again, they are moving randomly, but their velocities are quite low. So in other words, because they are moving very little, so these particles or this blue matter has low kinetic energy, and the red particles, they have high kinetic energy. Now because all these particles are moving, and when they move they collide with each other, so because red particles are moving with high velocities or high kinetic energy, when they hit this blue matter particles, they will transfer some of their kinetic energy to them. So in other words, when a red particle hit a blue particle, the red particle will slow down and the blue particle will speed up, because after getting hit with the energy, the energy will get transferred. So as we let these collisions take place, with time, most of the red particles will come in contact with blue particles, and in doing so they will transfer their energy to the blue particles. So after some time, what will happen is that the red particles will transfer some of their energies to the blue particles. So what will happen is that after some time, if we let these collisions take place, so both red and blue particles, so red particles will lose some energy, so their energies will be slightly lesser than before because they have transferred most of their energy to the blue, and blue particles will have gained some energy, so their energies will be more than before. So what happened in this process? Energy was transferred from red to blue, so energy transferred. And heat is the kinetic energy. So this kinetic energy is heat. So we can call this heat was transferred from red to blue. So now, as we can see that energy can only be transferred from fast moving particle to slow moving particle. The other way around is not possible. Or in other words, heat can only be transferred from high kinetic energy to low kinetic energy. So the transfer of heat always takes place from hot to cold. Okay, so in this picture we can see that an athlete gets an injury. So the trainer is putting an ice pack. So what's happening in there? So ice pack is not transferring cold to the body. That scientifically that doesn't happen. It's no such thing as cold. Cold is absence of heat. So what's happening here is the body, the athlete's body is transferring the heat to the ice, and because body is losing the heat, so its average kinetic energy is going low. So that's what's happening. Now temperature is not heat. Temperature is just a measure of average kinetic energy. So because the average kinetic energy of body is going low when it transfers the energy from the body to the ice pack, therefore the temperature of body or that part area will also go down. As we defined earlier, potential energy is the stored energy. Matter has potential energy as a result of position or composition. For example, a rock uh, placed at the top of a mountain or a hill, as shown in this picture, possesses high potential energy because of its position. High potential energy is unstable, makes a system unstable. So in other words, any system which has high potential energy is unstable. And in this universe, all objects, all systems would like to go from unstable position to stable position. Or in other words, they want to have as little potential energy as possible. So therefore, if we let this ball free fall, it will go from the position of high potential energy, which is on top of the mountain, all the way to the bottom, where it has low potential energy. So in other words, loses the energy. Now you may ask, how can it lose energy? What happened to that potential energy? So when it traveled, see, it was stationary here, so it carried all the potential energy in itself. So when it moved, so this motion, in this motion, now it has kinetic energy. So all the potential energy was transferred into kinetic energy, and once it came back to rest, now the kinetic energy was lost while it was traveling to friction and to something else. And then when it is at rest at the bottom, now it doesn't have any kinetic energy and it doesn't have any potential energy. So now this object is uh, as stable as it can be. So it has low potential energy, so that means it's stable. Matter has potential energy as a result of composition. It means that some matter are made up of those particles which hold potential energy in themselves. For example, particles of any fuel, they possess a lot of potential energy stored in them. So that's why when we burn the fuel, burning the fuel is a chemical reaction. That is a process in which we release all that energy. So fuels have high potential energy, and that energy is stored in them. Okay. So when a fuel particle, so imagine these are fuel particles or some fuel, and when we burn it, we let go these particles, plus energy is released. Now these particles have released the energy, that's why these particles are now stable, because they have low energy. All the energy is released, and we use this energy to cook our food or do some work for us. So that is different uh, uh, part of the discussion, but for now, just remember that fuel has a lot of potential energy stored in them. And The burning of fuel is a process in which we release that energy, and the same process make the fuel particles go from high potential energy position to low potential energy position, so they become stable. So the difference in that going from high potential to low potential is the heat energy released. Now, similar to fuels, carbohydrates and fats, which are present in our food, they act as a fuel for body. So these components of our food, carbohydrates and fats, they have high potential energy. So when they get digested and these components of food are metabolized, the products have low potential energy. The difference uh, in in these two states will release the energy which our body uses to do all kind of bodily functions. Let's take a look at this problem. Consider liquid water and water in gas state, which is steam. So first question is, how do these two states differ on the macroscopic scale? Now, macroscopic scale is the scale at which we see it. So we can see that liquid water is liquid, and so this one is in liquid state, the other one is in gas state. So that's obvious answer. Now, and steam is in gas state. Now, part B is explain these differences by describing the atomic scales. Now, this is more interesting. So, in liquid state, all water particles, they are randomly placed, but they are still in contact with each other. They are fluid, they are moving around. They don't have any order, but they are still in contact with each other. They are free to move. So that's what happens in liquid particles at atomic scale. But when it goes from liquid to gas state, now these particles are free from each other. They are not in contact with each other. There are large distances between one particle and another, and they are randomly moving again. In C, how does kinetic energy of particles differ from these two states? In liquid, it has relatively lower kinetic energy because they are not moving they are moving, but they are not moving that much. So their kinetic energies are lower. So in gas state, it has high kinetic energy. Last one is D, which state has higher temperature? And we know that uh, more kinetic energy means more heat. So more heat means higher temperature. So gas uh, state or steam will have higher temperature, and liquid water will have lower heat and lower heat and lower temperature compared to gas. Let's define what kind of energies these systems possess. So system number A is a compressed spring. Now compressed spring, like this way, so it has stored energy in them because of this compression. So any kind of stored energy is potential energy. So compressed spring has a potential energy. Windmill turning, so if this is the windmill and it's moving, and any energy because of movement, that movement energy is kinetic energy. So windmill turning is kinetic energy. C, particles in the gas state colliding with the walls of their container. Again, if particles are moving and colliding, So we know that any energy associated with the movement is kinetic energy. So these also possess kinetic energy. D, a skier skiing down the mountain. So skier is from top coming down to uh, uh, down a mountain. Okay, so again, as it's moving, and as long as it's moving, it says skiing down. It's not telling you that it was standing up and then now standing down. So if it's just stationary up at top of the mountain and stationary at the bottom of the hill, then that difference will be the potential energy. But now the skier is skiing down, so the skier is moving. So again, in this case, this energy will be kinetic energy. Last one is pasta prepared for a meal. So when you prepare a pasta um, for a meal, it's absorbing all kind of heat from the hot water, and that heat is getting stored inside the pasta. And when you, of course, when you eat that pasta, the stored energy will be released. But anyway, so this will be potential energy because it's the stored energy in the pasta.